Okay, why don't we reconvene? So our second session is on what we're calling computational causality. We have two fantastic speakers for this session as well. First, we have Sam Pimental. Sam is an assistant professor in the statistics department at UC Berkeley. We got two Berkeley faculty coming down to speak today. He received his PhD in statistics from University of Pennsylvania. Before that, a BA in computer science and mathematics from Stanford. His research centers on methodology for causal inference and observational studies. He develops new ways to form match comparison groups in large observational data sets using methods like discrete optimization. These tools allow transparent and interpretable inferences about the effects of interventions and provides opportunity to study the impact of potential unobserved confounding variables. And he'll speak today about causal inference using multi-level matching. Thank you, Sam.
Thanks so much, Jenny. Yeah, it's a real honor to be here. I'm excited to share some of this work. I want to kind of give a shout out to my collaborators on this project. Lindsay Page and Matt Leonard are both experts in education policy. And Luke Keel is another statistician. And we teamed up together to work on this project, which is a lot about methodology. But before I get into the methodology and talking about this multi-level matching study design, I want to say a little bit about the concrete application that helped motivate us. So what we were trying to do in this work is to evaluate the Myon electronic reader. So this is a commercial product that is marketed mostly to school districts and kind of school administrators for their students to use. It's basically an app that students can use to access a personalized digital library. It's supposed to help them get excited about reading, read more than they otherwise would. I pulled this sort of picture and this quote from their website, and the big claim here is that the Myon reader fosters student engagement and achievement. And obviously this is ad copy. This is not sort of in itself a well-substantiated scientific claim. And so we were trying to evaluate this and see empirically, does giving a student access to the Myon reader boost his or her reading comprehension? Or from a more sort of policy school district kind of perspective, if my school district, with its limited resources, chooses to invest in purchasing this app for students to use, at the end of the year, is this going to move the needle in our standardized test scores? Are we going to see some kind of measurable improvement in our students' learning? So, zooming out a little bit, both of these questions are causal questions in the sense that they ask about some intervention that we want to make into the world and what the effect of that intervention will be. So for the first question, we're asking, if we gave a particular student access to Myon and we followed them all year long and they took a test, how would the score on that test be different from if the same student had not had Myon access and had to take the same test? And so the challenge here is that we can never really design a study that will let us see both those numbers. We either have to give Myon access to the student and let them use the reader and then take the test, or we have to deny that to them. We can't have them take the test under both conditions and compare those numbers. So this is sometimes known as the fundamental problem of causal inference. You can't see both potential outcomes of your intervention. And so this is what we're trying to work around in some way using statistics or using smart kind of study design strategies. So obviously kind of the gold standard way to approach this problem is using a randomized trial. And you can imagine a really simple randomized trial to evaluate Myon. You get a bunch of students who agree to participate in your study. For each one, you flip a coin. If it's heads, you give them Myon access all year long. If it's tails, you tell them, sorry, no Myon access for you. And then at the end of the treatment course, we have two big groups of students. We have them all take the same test and compare their reading scores. So what's kind of magic about this and what makes it a nice way to do causal inference is that the randomization gives us a guarantee that these two groups of students are going to be similar in essentially every way as a group, except for this Myon intervention that differs between them. And this is because these random coin flips we're doing to decide who gets which intervention are completely blind to everything about the students. There's no way this coin flipping procedure can systematically sort more disadvantaged or more engaged students into one of the two arms. On average, everything is going to be similar between these groups besides the treatment itself. And so we can attribute any systematic difference in test scores to that treatment. All right, so probably this isn't new to most of you. And this is fine. You know, if we could have done this randomized trial, that would have been great. We couldn't. We had observational data instead. Basically, Wake County, North Carolina, the school district there, had data on a bunch of summer school students, some of whom had access to this Mayan reader and others who didn't. So we got a hold of this data. In this data, it was pretty clear that Mayan access, we didn't really get the full story about how individual students had gotten this Mayan access and others did not, but it was pretty clear it wasn't random because we could see systematic differences just measured in the data between the groups of students who received access to the reader and those who didn't. In particular, students without Mayan access tended to have slightly lower test scores for the year prior to summer school, and they also were more likely to have limited English proficiency. So obviously this is a problem. If we just do kind of a raw comparison of test scores between the two groups, then what we're going to measure isn't actually the causal effect of having access to the Mayan reader. It's going to be a mix of that effect and these other underlying differences due to the fact that the student groups weren't comparable to begin with. So the question for me as a statistician at least is there a way we can use this data, can we transform it to be more like a randomized trial and to give us a comparison that will be more compelling as a causal inference? So this gets us to matching, which is one of my favorite things. It's basically a study design, a very simple idea, where we take observational data like this, where you have a treatment group, in our case the Mayan students, and a control group, which is the non-Mayan students, that look systematically different on observed variables. And you select a new, smaller control group out of this large control group that looks similar to your treated group in unobserved variables. And usually the way this is done is via pairing. So we'll take each Mayan student in our data and pair him or her to a similar control student. And then we'll focus on these pairs for analysis, and that will tend, all the variables we pay attention to when we pair up these students, assuming we're able to form good pairs, those variables will all be brought into balance, and the data in this smaller paired group will now resemble what we might have seen in a randomized trial. So the idea is to make the data look like what we would have seen in a randomized trial, even though we can conduct it. So that's not the same thing as actually having a randomized trial. There are important assumptions that we need in order to close that gap, and I'll get back to those later in the talk. But to be already in the Mayan data, we have another complication, which is up until now, in my discussion of this Mayan treatment, I've been talking as though individual students were selected, either randomly or some other way, to receive access to Mayan or not. But in fact, that's not how these decisions were made in Wake County Public Schools. Instead, Mayan access was given as a whole to individual schools or denied to an entire school. So if you happened to go to a school that got Mayan access, you got it, and if you didn't, then there was no way for you to get access to Mayan. So this introduces a kind of a disconnect into our study design, where we're still interested in individual students and the impact of this intervention on them and their individual test scores, and we have data about that. But treatments are not being given to these individual students, they're being given to big groups of students all at once. So, so one thing that comes out of this is the simple randomized trial I described a few slides ago, where we individually randomize students to treatment, isn't really the appropriate thing we want to copy here, because that's not really how this treatment is going to be given out. Instead, what we probably want to copy is something called a cluster randomized trial, which is just flipping coins at the school level instead of the student level. So, so cluster randomized trials, there's some very statistical things that are different about them than randomized trials, but big picture, it's the same idea. You just have to, you just flip a coin for each school, and it buys you a similar guarantee that school variables and student variables will be similar, assuming you have enough schools in a large sample, and you can, and the comparison of average student test scores between your two groups will still give you a measurement of causal impact. So that's kind of what we're aiming to approximate, but now the question is, how do we match in a way that's going to approximate this kind of trial? Now that we have these two different sort of levels of analysis present in our observational data. So this is what I really want to talk about today, is the multi-level matching design, which is to a cluster randomized trial in some sense, as the simple matching or common matching design is to the individual level randomized trial I gave an account of right at the beginning of the talk. So in order for the multi-level matching design to kind of reshape our data in a way that represents a cluster randomized trial, there's a few complications we have to deal with. The big one, of course, is that there are these two levels, and variables measured at both of them that may be out of balance. So we need some kind of study design that's going to solve imbalances at both those levels. This means we need a special kind of structure for our multi-level match, and that makes it a little more complicated to actually construct the match. So I'll talk a bit about how we solve that problem. Sorry.
Did all students in a treated school get the...
Yeah, so this is a good question. The treatment here is access to Maya. So all students in the school had access to Maya. We don't necessarily know that they all ended up using it or how much they used it. If we'd had extra data on that, then we could have perhaps done like an encouragement design, instrumental variables type stuff. But yeah, the access was given in this way, so we know how that was distributed. Right, and so that actually relates to the next thing, which is once I've kind of given an account of multi-level matching, I want to talk about this arrow here. What is the gap between these matching designs and randomized trials? What things need to be true in addition in order for these things to give us to estimate the same effects that we would have estimated in our randomized trials. And then at the end, I'm going to talk about how this all applies in the Mayan study, and also some analyses we can do to assess robustness to these assumptions, which I think is one of the most important parts of working on causal inference from observation data. So this is the roadmap of where I'm going. Maybe I'll pause here and see if there's any other big picture questions before I dive in. Okay, great. So let's talk a little more about the Mayan data. Again, this is an observational study. So the first thing we need to look at before we try and do causal inference is the variables we've observed about our students and our schools, and look for these systematic differences which are going to introduce bias if we don't do something about them. So we have a bunch of school variables measured here, things like average attendance at the school, percentage of staff turnover. We know the percentage of students at each of these schools who receive free or reduced lunch, which is a proxy for socioeconomic status. We also have a smaller number of student variables, including their past test scores, whether they're in special ed, their race, their gender. And because it's an observational study, the schools in our two groups may be different in various attributes between the Mayan group and the non-Mayan group. The students in the Mayan schools may also be different from those in the non-Mayan schools. And matching strategy needs to be able to fix both these levels of imbalances before we have a compelling case for causal inference. So, a first attempt at solving this problem might be just to try matching treated schools to control schools in the same way that we went from flipping coins for individual students to just flipping coins for schools. And then we could, this would be easy to implement. You could easily use this exactly the same software used to match students to match schools, and then compare average student outcomes with the schools. The problem with this is it doesn't deal with the student level variables, right? Even if you match two schools and make school pairs that are comparable on school variables, that doesn't necessarily fix imbalances at the student level. You can try turning student variables into school variables by aggregating, but in doing that, essentially you're going from a data set of 1,500, I think that we actually have about 3,500 students, down to a data set of 50 schools, and you're just throwing away all the granular student level information that you had in the original data set. So we really wanted to find a way to use this granular student level information and try to remove those imbalances, but still preserve a student level analysis. And so this gets us to the multi-level matching. So we didn't actually come up with the original idea for this. That's from an earlier paper by Zuckerberg and Kiel, where they kind of laid out this structure for a multi-level match. And the idea is that we have school pairs, as we talked about just a minute ago, but that within each of these school pairs, we also match students. So if school A receives treatment and is paired with school B, which did not, then in addition, all of the students in school A who had access to this Mayan treatment are going to be paired to a similar buddy student in school B who didn't have that access. So what these two levels of pairing gets us is that in this first step, we can make sure we're comparing schools with similar attributes. But then anytime we look at students within these two schools, we also have a guarantee that there's someone with similar student attributes in their school. So this is kind of what we're aiming for. This is the design we're trying to construct. And again, the purpose is to transform our data so that we have balance at both the school and the student level as we would have this trial. So before I talk about how we built this design, any questions at this point?
So if I understand correctly, it's like you're taking all the students out from the control schools, right? And matching with all the students from the treated schools, right? But don't we care about like the boxes that they're in? Like, isn't it important that like you're also like a blue dot that's one of 3 blue dots, so it's like 1 of 2 blue dots per school? Right? Like there might be a school level variable that's like, right? Like if your school is very large, for example.
Yeah, I mean that's part of. I think this design preserves the ability to look at that, right? If you had a very large school, say, then at this level you'd want to be matching large schools to large schools, right? So if you had a very large treated school, you want to match it also to a very large control school, and then within that school pair, you could pair these students to those other students.
Maybe I misunderstood that.
Okay, yeah, maybe.
So is this process sequential? You find the best match for one school, and then you start looking within that other school that's the best match within the students that are the best matches?
No, and that's what I'm about to talk about. And that's where the optimization comes from. But again, this is just we're aiming to end up with something like this.
How do you define the best match for the schools? Are you trying to infer how they might be receiving the program, or is that how you?
Yeah, this is a really good question. So when I get to the part where I analyze it, then the way we're going to do inference here is we're going to look at these school pairs and we're going to treat it like this was a randomized experiment and we just flipped a coin to decide which of these 2 schools got treated. So from that perspective, what you want to optimize here is kind of a school level propensity score, and that would be sort of a natural choice for what to match on here. So you want to think about what things influenced whether this school got the Mayan access, and then those are the primary variables you might want to emphasize. I guess there's other perspectives you could take, but I think that's the place to start. Great questions. Okay, so let's get back to this question of how we actually construct this match. So before I get to that, let me talk about matching at one level first. You can set up matching in a sort of individual level treatment problem as just linear optimization, basically. Again, what we're trying to do when we form these pairs is make group individuals who are similar on their pre-treatment attributes. The starting point is to define some kind of similarity metric between attributes. You have to know when you look at 2 people what it means for them to be similar or not. Propensity score is one way you can do that. There's kind of the literature about other similarity metrics, which I don't have time to get into. But once you define your similarity metric, then you now any 2 units you pull out of your study, you have some measure for whether they're similar or not. Small numbers mean they're similar, big numbers mean they're not. And then you can just plug this into a linear optimization framework and find the set of pairs across all possible pairs of your data that gives you the lowest total similarity. And that's a very standard problem in optimization. And we can use existing solvers to do that. So at the individual level, once you define your similarity metric, this problem is straightforward. For the multi-level match, it gets complicated here because even though we can define similarity metrics at both the school level and the student level based on school attributes and student attributes, these 2 optimization problems are now kind of entangled with one another. So depending on which school pairs you select, it's going to limit your choice of which student pairs are available and vice versa. So there's a question here about whether we just do this sequentially. It turns out if we do that sequential process and we pair up the treated schools first and then just at that point step down to the student level and match up the students as best we can, we might get into trouble. It could be that even if these schools look comparable in school attributes, that their student populations actually don't overlap very much. And now you've painted yourself in a corner and you're stuck with a really bad match in these schools. So the optimal way to approach this is actually to, you have to sort of collect information about the student level similarity within school pairs and let that trickle up to the top level before you do that pairing. Again, this is an idea that goes originally back to this Similarity Metric paper, but in our work on the Mayan study, we developed a more specific algorithm that runs a lot faster. It basically looks something like this. So we start by looking at the students in each of the schools, and in particular, we consider every pairwise combination of a treated school with a control school. And we'll look at the quality of the match we obtain there and summarized using a score. So we'll do this for treated school 1 and all of the different control schools. That gives us a column of scores. Then we'll repeat it for treated school 2, which gives us another column for treated school 3. And this develops a whole matrix of students' population similarity across schools. So this can be kind of a computationally intensive step, but this can be done in parallel, right? Because each of these comparisons is independent of the other, so you can get some speed up there. And the nice thing is once you're done here, you now have this matrix that kind of neatly summarizes the quality of the student level matches. You can then combine that, say, do some kind of weighted combination perhaps with the school level dissimilarities based on school metrics or school attributes. And now you can do this top level match in an optimal way. And once you've done that, you can just look up the match you did earlier for the students, and you have your optimal match structure. So again, the big picture idea is that we can't think about these two optimization problems in isolation from one another, or just do them sequentially. We have to think about it in a joint way and find a way to combine those two sets of information to get an optimal match. Okay, so this is, again, this structure is what we're aiming for, so we can approximate the cluster randomized trial. This is an algorithm that lets us do that in an optimal way. So now we've got our multi-level match. What should we be thinking about before we just present an estimate as a causal inference? Oh, I forgot to mention, we have an R package that does this, match multi, so please check it out. And there's a paper that has some extra features in here, which you can use to improve the performance of this and get an even better balance than you would expect in a statistics approach. Again, more details in the paper. Happy to talk about that, data perception or so on. Okay, so yeah, let's get back to those assumptions. Again, this isn't doing the same thing as a cluster randomized trial. Even if the data you get out of a multilevel match design, the observed data looks similar to what you would see in a randomized trial, it's not the same thing. And the assumptions we need to make to close that gap are, first of all, no unobserved confounders, right? And, you've been hearing a bit about causal inference today, so this is probably a theme you're noticing by now, is that anytime we have observational data and we're trying to do causal inference, with a few very special exceptions, we need to make this assumption that you've measured all of the variables that are important, that explain important differences between the two groups. Right? If in our data, say, the Mayan students or the non-Mayan students are getting high levels of private tutoring compared to the other group, something that Wake County wouldn't have data on, then we're in trouble because we can't remove that by matching. We don't know about this imbalance because we can't see it in the observed data, and so it's going to remain even in our match design. If there's no unobserved confounders, then, and if in addition we don't match on post-treatment variables, meaning we don't, say, match on test scores collected halfway through the summer after people have already been experiencing a treatment effect, remove some part of our effect. And if in addition there are no cross-school peer effects, meaning, if I go to school A and get Mayan access, I'm not going across town over the weekend to my cousin's house and sharing my Mayan app with them, so their test scores improve too. Assuming none of that is going on, then the effect that we get after a multi-level match comparison is going to essentially be the same as what we would see in our randomized trial. And so now we can claim that we have causal inference. But these assumptions all have to hold.
So it's all be measured at the student level?
No, it's measured individually at the student level.
So that means we can probably do some cross-level interaction between students if you attribute at school level variables.
Sorry, say that again.
Like, can we do some cross-level interactions?
I see. So you're saying, could we think about fixed effects for schools at some time?
So it's more so can we plot the treatment effect to vary by student level attributes?
Oh yeah, right. Yeah, that's actually a great point. That's one of the advantages of this design, right? Because you actually have the student level here, then if you cared about the effects for certain types of students, you could then break this down into, say, different categories of students by their past test score performance or by their demographics, and you could break out those subgroups. If you aggregated everything up at the student level, the school level, you lose out opportunity. So that's another advantage of this design. It's a great point. I want to say a little bit more about peer effects here. It turns out this peer effects assumption is something we need not just for observational studies, but you actually need this in the cluster randomized trial as well. You don't have to worry about these ones if you're just running a randomized trial, but these peer effects will still mess up your causal inference even in a randomized study. The other thing that's interesting about these peer effects is that this assumption is different for clustered studies, like the cluster randomized trial and multilevel match, than it is for individual level randomized trials. And in particular, if you were doing an individual level study, you need a much stronger version of this. If you were flipping coins for individual students to do your randomized trial, you would need to assume that no individual student had any peer effect on any other. And for something like the Mayan study, that's probably a way too strong an assumption. If students are in the same classroom all day, every day, some of them are using Mayans, others aren't, there's bound to be some kind of peer effect. Here, the kind of the cluster treatment makes the story work a lot better in terms of forgetting peer effects, because we only have to for cross schools. Okay, so those are the assumptions. If these things hold, then we can get something we trust as a causal effect out of this multilevel match design. So with this in mind, let's look at the Mayan data again. Again, we have about 3,500 students here in Wake County, over 50 schools. Okay.
What is the causal effect you're seeing? The average effect in the treated, ATT?
Great question, yeah. So this is going to be the average effect on, so I guess it sort of depends on the details of the mesh design a little bit. The ideal case is we get to keep all of the treated schools and all of the treated students. We may lose a few students, but often we're getting kind of close to that. And so then basically what it is ATT on the treated schools. The matching is kind of making sure we select controls that are similar in their sort of covariance to the treated schools. And specifically we're measuring the ATT of giving Mayan access to an entire school. And in that way we kind of assume any pure effects.
So it's not the effect on the student?
It's an effect on the student, but it's an effect of a treatment that's given to a school. So it's the effect on you as an individual student if your school receives the Mayan access. Yeah. So this is one of the tricky aspects of the cluster design. That's a great question. Okay, yeah. So back to Wake County. So this is what we're trying to measure. We're trying to measure the impact on an individual student of their school getting this Mayan access. Initially, the data is imbalanced, so we're going to try and do a multi-level match to fix these imbalances. After the match, we end up with a much smaller data set. We're down to only 16 school pairs and about 1,500 students. But this data set is actually much better for measuring causal effects because we get much better balance. So this is a balance table showing the difference on various school variables between the groups before matching and after matching. These differences are measured in standard deviations between the group means. And you can see I put in bold here a bunch of standard differences that are bigger than a fifth of the standard deviation. If we have sort of a good randomized trial with a large enough sample size, we don't expect to see many or hopefully any of the standard differences this large. But in the raw data, we're seeing a bunch of them on important variables like percentage in English, past test scores. After matching, the numbers haven't gone down to zero, although they wouldn't have gone down to zero in a randomized trial either. But they're small enough that now this data looks much more consistent with what we might have seen in the randomized trial. And we get a similar table for the student level variables. In this data, it turned out the student level variables actually weren't that imbalanced to begin with, so we didn't have a lot of work to do here. Again, big picture, the multi-level match design, what it guarantees us is that if there were big imbalances here, the design would have improved those as well. And that student level matching step would work hard to remove any such imbalances as well. All right, so we now, in this multi-level match design, we have data that on all the observed covariates looks reasonably balanced, which is what we would expect out of a randomized trial. So now, if we make these assumptions as well, we can go ahead and analyze this as though it were a randomized trial and take causal effect estimate and significance. So the effect estimate is pretty easy. You can just look at the difference in test scores between the treated students you selected and the control students you selected. I'm a statistician, so it's important to me to get a p-value and a confidence interval for this stuff too. And it turns out that you can use sort of versions of a standard t-test for cluster data, and that will give you pretty good answers. But I want to talk about a slightly different test, which has some statistical advantages, and I think is really intuitive and nice, which is called a randomization test. The idea is, if our assumptions hold, then within these school pairs, the two schools are equally likely to have received Mayan treatment, in the wild in our observational study. And so what that means is we can generate a null distribution for a test statistic by erasing the labels of which schools are treated and which are controlled and then by flipping a coin independently for each of our pairs, and randomly reassigning these labels. And then, based on this sort of random fake data we generated, we now we compute our test statistic again. Then we flip the coins again and get a new version of the test statistic. And we do this repeatedly, flipping coins over and over again, and generate this whole family of null test statistic values. We then compare the original observed test statistic, the actual data, to this null distribution value. So when we do this in the Wake County data, I guess first of all, the effect estimate we get is 1.2 points. So Mayan students did 1.2 points better on the standardized reading test we gave in the summer than non-Mayan students. The range of reading test scores in the raw data is from 235 points to 616 points. So that gives you a hint about where this is going. Our p-value indeed was only 0.3. About a third of these null odds we got were more extreme than the actual estimate. So we didn't find any strong effect of Mayan. And in fact, this confidence interval allows us to say something a little stronger than just we didn't reject the null. Talking to my co-authors who are experts in education policy, we kind of figured that in order for Wake County or a similar school district to be interested in this intervention, they want to guarantee at least some minimal effect size, which we figured would be, say, 1/5 of the standard deviation of all reading scores. In our data, that was 11.7 points. The confidence interval actually rules out any effect that large. So we're not just saying we can't reject the possibility of zero. We're saying, with confidence, our data is actually inconsistent with any sort of effect of interest in this. Okay, so assuming our assumptions hold, this is the end of the story. We looked at our data, we adjusted it, so it looked like it came with a randomized trial. We came up with a causal effect estimate, and we did our inference. Happy ending. But to be really honest, we should think harder about these assumptions. So let me just say a couple brief things about these assumptions. The big assumption we're worried about here is the unobserved compounder assumption, because again, this is administrative data we got from Wake County. There's all kinds of things that affect students that could be different between the Mayan and the non-Mayan metric. So let's say there is some unobserved compounder in our data, and our estimate from this match is wrong. What we're really concerned about is that there's bias here that's masking a true large effect of Mayan readings. It looked like there was no effect, but maybe that's a product of the bias, and the bias is hiding something that a true positive effect, say, we can't actually adjust out for this bias because, by its very nature, it's unobserved. What we can do is a sensitivity analysis where we ask, how big would this bias have to be to throw us off? So I don't have a lot of time to talk about the details of this, but basically what we do is we go back to this inference procedure. Here, to get our p-value, we flipped fair coins in each of these match sets. We're now going to allow those coins to be biased, and we're going to allow them to be biased in an adversarial way, which will change our effect estimate as much as possible. The details of this kind of analysis are all laid out in a testing book by Paul Rosenbaum, which I give you the reference to. Anyway, for any level of bias that we pick, a certain amount of bias in a coin, we can get a new wider confidence interval that says how much our results will change. And what's a little bit depressing is that although we had this nice effect, that the true effect was no larger than 1.7 in either direction, in assuming all our assumptions hold exactly, if we let this bias, even a little bit of bias creep in, if this goes up from 1 to 1.16, then all of a sudden the confidence interval now includes this minimal effect size. So this puts an important asterisk on everything we've done. It says if these assumptions are exactly true, then there's no effect of Mayan. But a small amount of bias could be hiding at least a small effect. Again, maybe that's not an exciting thing to write a paper about, but I think this is really good to know if you're actually trying to understand the world and do science with observational studies. So that's about all I've got to say. Big picture takeaways are, you want to think about the randomized trial you would like to conduct when you're doing causal inference. Matching is a way that you can design your study kind of along those principles. And multi-level matching is a way to do it for clustered studies. Finally, you should know your assumptions really well, and you should do sensitivity analysis if possible. There's other cool things we can do with multi-level matching, and we're trying to explore. Happy to talk about those later. I'll stop now. Thanks very much.